morning, everyone. Thank you for coming to the class. Today we will continue the concept of probabilistic analysis that we started on Monday. If we have time, we will start solving some problems which are similar to the problems that we have in the homework. So this week on Friday or maybe on Thursday, I'm not sure which one. More probably Friday, I will post a new homework. This new homework which will be posted on Carmen this week is a tricky homework. We will have 2 weeks to finish this homework. I will also post a practice problem, 14 problems with solutions on Carmen. And also on Friday that you come, we will start working on the new extractivity number 3. So grader has told me that it seems that she has finished grading for extractivity 1, then your grade for extractivity 1 should be on Carmen. I will return extractivity 1 back today. And when she finished grading extractivity 2, I think your grade will be on Carmen. So as I explained at the beginning of this week on Monday, concept of probabilistic analysis that we will see this week next week is a tricky concept and very challenging concept. Maybe one of the most challenging concepts that we have in Foundation 2 is this concept. So then first we will finish our analysis for hiring manager problem that we explained about. Then we will solve some problems which are similar to the problems that we have in the homework and in the exam. Excellent. Next number 3 that we will see on Friday also contains some problems which are similar to the problems that we will see today and this week. So what we want to do very quickly about something that we did on Friday. As I explained on Friday, concept of worst case and best case running time that we had in Foundation 1 always doesn't give us very realistic running time. For example, we explained about the problem that we want to hire an employee, and the process was like this. You have N candidate, you pay an agency to send you these candidates, you will interview these candidates, and based on their quality, you hire them. And the process of hiring is like this. If you hire one employee, you do not stop hiring. You do not stop hiring and interviewing. You continue the process of interviewing until all N candidates are interviewed. And if candidate which is being interviewed is better qualified than the current employee that we have, we follow the current employee and we hire this candidate. But we do not stop the process of interviewing. It means that tomorrow again we will interview another candidate and we continue the process. As we explained, our goal was to estimate the cost of this process. We had 2 costs. One cost which should be paid to the agency to send us the candidate. This cost is not big. And another cost is cost of hiring. Because if the candidate which is being interviewed is better than the current employee that we have, we hire this person. And when we hire this person, we need to pay. Therefore, as we explained, we have 2 costs, and based on the number of people who are interviewed and number of people who are hired, we can have this estimation of our cost. N is the number of candidates, M is the number of people who are hired. Then if CI is the cost of interviewing, CH is the cost of hiring, then that's our estimation of cost. So as we explained, M is not noun because we do not know anything about the quality of these candidates before interviewing them. Then we want to see what estimation we can have about M. We explained about worst case running time. As we explained, worst case occurs when these candidates who come are increasingly sorted in their quality. It means that the first candidate is the worst one, the second one is a little bit better, the third one is a little bit better, the last one is the best one. In reality, it never happened, because in reality, when people come for interviewing, the quality of these 10 people is distributed randomly. When we do not consider this randomness, we consider very extreme case. Extreme case means that these people are sorted increasingly. And when we assume such a extreme assumption, then we will reach to the worst case running time that we explained about, which is O of n. So, as we explained, this procedure means considering the worst case running time, since it is based on very extreme assumption, is not very realistic. Then in order to have more realistic estimation, then we consider the randomness is there. It means that these candidates are distributed randomly, and we do not have any idea about their quality. Then what was our goal? Our goal was to find the estimation for our cost when this randomness is considered. That is our goal. Okay, this is very quick review of something that we did on Monday. Any questions? Okay, so we had some concepts from mathematics, as we explained. When randomness is involved, always you consider probability theory. Means that probability theory makes sense when something is chosen randomly. If nothing is random, then probability doesn't make sense. So then we borrowed one concept from mathematics, which is the concept of the indicator function. As we explained, indicator function for an event is defined in this way. If A occurs, IA is 1. If A doesn't occur, IA is 0. And then we explain this important fact, easy fact, that if by using indicator function, if you define a random variable, then expected value of random variable is same as the probability of A. We had these, and then we solved one easy example that if X is the number of head, when you roll n, when you flip n coins, then we can decompose X as the sum of these xi. Xi is defined as the indicator function when we have head in ice flip. It means that in ice flip, if head occurs, I of xi is 1, and if head doesn't occur, means if tail occurs, xi is 0. That's something that we use. And then we evaluate E of X, expected value of X. As we explained, expected value means our expectation of X, because number of head is not known. Before flipping a coin, before flipping n coins, you do not know what is number of head. Then expectation here makes sense. Again, one more time. If something is certain, expectation doesn't make sense. When you are uncertain about something, expectation makes sense. And in this case, I am flipping n coins. I do not know what is the number of heads. Then I will evaluate my expectation. And as we explain, expectation here is n over 2. It means that if everything is fair, our expectation is that half of the elements, half of the flips will be head, half of them will be tail. That's something that we have here. Now, what is my goal? My goal is also we explained about harmonic sum. As we explained, harmonic sum is one concept that we had in Foundation 1, and some of you may have seen it also in Calc 2. If you took Calc 2, then we explained that when harmonic sum is defined as this sum, and if we want to consider the asymptotic behavior of harmonic sum, we can say that asymptotically harmonic sum is same as log of n. And we explain what it means in calculus. It means that although harmonic sum is a divergent sum, but since log of n doesn't have very strong asymptotic behavior, then we can say that the asymptotic behavior is this harmonic sum is not very strong. What it means that although this guy approaches to infinity at infinity, but this infinity is a scheme infinity. That's something gigantic. That's something that we explain about. Okay, I believe we are ready to see our main goal. What is our main goal? If we come back to the example of hiring a new employee, our main goal is to compute the expected number of times that we hire a new office assistant. Our goal is to find our expectation of the number of times that we hire a new office assistant. Please listen to me very carefully. Why here expectation makes sense? Because number of times that we hire is not noun. Why it is not noun? Because before interviewing, we have no idea about the quality of candidates, because we assume that these candidates are distributed randomly. Then I do not know if, for example, how many of these candidates will be qualified to hire. Then the number of times that we hire is not noun. In mathematics, we say the number of times that we hire is a stochastic, because randomness involved. Therefore, the number of times that you hire a new employee is a stochastic. Therefore, expectation here makes sense. That's the reason that I use the word, I want to emphasize on the word expected number of time. If you know how many people will be hired, the expectation doesn't make sense. Since here I assume these people are distributed randomly, then expectation makes sense. Therefore, I want to find my expectation of number of times that we hire a new office assistants. Okay. We will use some concepts from statistics. Listen to me very carefully. If this looks a little bit strange, that's understandable. Let x be a random variable whose value is equal to the number of times we hire a new office assistant. We didn't do anything here. I'm just trying to explain the problem in the formal math notations. We assume x is the number of times that we hire. My goal is to find expected value of x. That's something that we explained before. In order to evaluate expected value of x, I will decompose x into xi's. In what way xi's are defined? I define xi this way. If candidate I is hired, xi is 1. If candidate I is not hired, xi is 0. You can see two scenarios. Here, xi is a function. You have n candidates. If candidate I is hired, xi is 1. This is exactly like the example that we had on Monday, that you flip n coin. If in i's flip you have head, xi was 1. If you had tail, xi was 0. Here we defined exactly the same thing. If the candidate I is hired, xi is 1. If the candidate I is not hired, xi is 0. You can say very easily that x, which is the number of times that you hire, can be decomposed as the sum of xi's, means x1 plus x2 to xn. Remember that some of these xi are 0, some of these xi are 1. But when you add these ones, means you have 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1. When you add them, the number of these ones will give you the number of times that you hire. Any questions? Any comment? Maybe I am not pronouncing some names correctly. I am learning. Please forgive me. Fiona Van. Also, each one is not a key. John Lasser starts with E. So, let's continue. We will continue with this, okay? Let's teach a little bit. Okay, so then I could decompose x into these xi's. Remember that these values that you have on these xi are 0 or 1. If you hire, for example, for x1, if the first candidate is hired, x1 is 1. If the first candidate is not hired, x1 is 0. Same story for x2, same story for everything. Okay? Then when you add these ones, you will get the number of times that you hire. Now our goal is to evaluate expected value on x. Expected value of x is the sum of expected value on xi's. But since xi's is defined as indicator function of this event, means that we hire candidate I, we can say that this expected value is probability of hiring candidate I. Then, in order to continue, we have to evaluate the probability of hiring candidate I. Any questions and comments? Any questions? We just need to evaluate probability of hiring candidate I. Let me ask you this question. What is the probability of hiring the first candidate? What is the probability of hiring the first candidate? Yes, please. What was your name? Logan. Yes, thank you. But can you explain for us why the probability of hiring the first candidate is 1? Because as we explained, thank you very much, Logan. As we explained, we really want to fire our current employee. We hate this person and we want to get rid of this guy. Then it doesn't matter how much the first candidate is terrible. Definitely we will hire the first candidate because the current employee should be fired. Then it doesn't matter how much the first candidate is bad. The first candidate definitely will be hired. Then why? Because we can say that the first candidate will be happy at least for 1 day. Because for 1 day, he or she can say, I have a job. Then the probability of hiring the first candidate is 1. What is the probability of hiring the second candidate? 1.5. Yes, thank you. Exactly.
Let's be 2 people and like you have 1 option.
Thank you. You want to find the probability of hiring the second candidate. You are comparing how many people? 2 people. The guy who was hired yesterday and the person who is being interviewed today. We are comparing 2 people and the probability of choosing one of them is 1/2. Since you are comparing between 2 people, probability of hiring the second candidate is 1/2. What is the probability of hiring the third candidate? Again, the same logic can be used because we start yes, 1/3, exactly. You are comparing 3 people, and among these 3 people you want to choose 1, then you can say the probability of hiring the third candidate is 1/3. Fourth candidate, 1/4. Fifth candidate, 1/5. Do you see that probabilities are getting smaller? Because 1 is bigger than 1/2. 1/2 is bigger than 1/3. 1/3 is bigger than 1/4. Why? Because for sure, when the number of people who are being compared gets bigger, probability also gets smaller. Because the chance of getting higher is getting smaller. Then what we can say? Probability of hiring I's candidate is 1/I. Therefore, here we can say that this probability of hiring the I's candidate is 1/I. First candidate 1/1, second candidate 1/2, third candidate 1/3, go to the n's candidate 1/n. Any questions? Any comments? Any questions? That's a very, very good example, actually. That's a very good example. And I have stolen this example from CLRS. Very, very good example. So I have evaluated my expectation of the number of times that we hire. My expectation of number of times that we hire is this sum, which is a famous sum. As we explained today and on Monday, is sigma is the harmonic sum. As you may remember, when we wanted to evaluate the running time, we wanted to find the asymptotic running time. Here's the same story. We do not want to find just our expectation. We want to find the asymptotic behavior of the expectation. And as we explained, asymptotically harmonic sum is same as log of n. Then asymptotically harmonic sum is same as log of n. Then here what we can say that our expectation about the number of people that we hire asymptotically is same as log of n. It means if, for example, you have, I don't know, for example, 10 candidates, you will evaluate the log of 10. And that's your expectation of the people that you hire. So what was worst case running time? O of n. What is expected running time? Our expectation of the time that we hire is log of n. And here, as you can see, log of n is weaker than n. And this is true always. Means that expectation running time, expected running time is smaller than, is weaker than worst case running time. They can be equal, we will solve examples today, and they can be sharp. It means that here, as you can see, log of n is sharply weaker than worst case running time. Any questions, any comments? Okay, I'm not sure if I am pronouncing correctly. Justice, last second. Alicia, again, I'm not sure if I am correctly. Ion, I-N, A-Y-O, if I can read it correctly. E-N. So, Charles. And who last time is not on T? Okay, so hope this problem gives you the good idea to differentiate between expected running time and worst case running time. This example is very good example to give us the idea for differentiating between these two concepts. What kind of problems we will have in the exam or in the homework? This is the kind of problem that we have in the exam and in the homework. Let me explain about this problem. I think today if we solve this problem and one more problem, you will be ready for extracurricular on Friday. So, okay, let's see what we have here. Here, okay, we want to find the asymptotic worst case and expected running time of this function. In the function, as you can see, input is A, an array, n is the length of array. You assign 0 to s, k is chosen randomly out of n number. You have two for loop, and we want to find the asymptotic running time, best case and expected. First, let me explain why expected running time makes sense here. Expected running time makes sense here because k is chosen randomly. If no randomness involved, expected running time doesn't make sense. Again, remember something that I explained, and you will hear this from me a lot until the end of this chapter. Randomness is the key word for finding expectation. If nothing is chosen randomly, it doesn't make sense if you say, what is your expectation? It is exactly like the example that we had before, finding example. If election is not election, like my country, means the winner is known 2 years before election, then in this case, it doesn't make sense if somebody says that, what is your expectation of the winner? People would laugh. Winner is known. Then what does it mean? What is your expectation of the winner? In countries that election makes sense, election had a meaning, then you can talk about expectation. Exactly the same story here. Means if nothing is random, then it doesn't make sense if someone says that find the expectation. Expectation is the worst case. They are the same. In this case, since k is chosen randomly, because if you ask me in line 2, what is k? I do not have any certain answer. K can be 1, k can be 2, k can be 3, k can be 4, k can be n minus 1, k can be n minus 2. Then I have no idea what k is. Why it is important? Because if you ask me what is the number of iterations of the first 4 in line 3, I would say k, but I don't know what is k. Same story for the number of iterations in line 4 for the second 4. Again, number of iterations, I would say k to the power of 1/3. Again, I do not know exactly what is k, and I do not know exactly how many iterations we can expect. What we will do, first we will evaluate worst case. When we want to evaluate worst case is based on extreme case. K is chosen randomly out of n number. What is the maximum value for k? N. The maximum value for k is n. Therefore, the worst case running time also is n to the power of 4/3. Because for the first 4, I assume k is n, I am evaluating worst case running time. For the first 4, n. For the second 4, n to the power of 1/3. Then, sorry, but here we have it, but this floor should be between k to the power of 1/3, not k to the power of 1/3. Then here, I am plugging n equal, k equal n. Then the first 4 we get this sigma, the second 4 we get this sigma, we evaluate this sigma, that is easy, you will get n to the power of 4/3. That's the worst case running time. For the worst case running time, we assume k is chosen as the maximum possible value. What is the best case running time? Worst case 10 to the power of 4. Best case means the minimum number of evaluations, minimum number of iterations. Don't be shy. What is best case? 1, thank you. What is your name, my friend? Kaden, thank you. Then here we have 1, because k can be chosen out of 1 to n, then we assume the minimum value 1, then we have just 1 iteration, then done. K is 1. So this is worst and best. Then worst is n to the power of 4/3, best is n constant. What is the goal? The goal is to find expected case. For expected case, I would like to write on a board. As you can see, solution with all details is on Carmen, but writing on a board is better. You can explain it step by step. In this algorithm, we have 2 4. For the first 4, number of iterations is k. For the second 4, number of iterations is k to the power of 1/3. K is chosen randomly out of 1 to n. That's the values that k can accept. My goal is to find expected value for the running time. I will denote x. X is what? X is number of iterations. Number of iterations. Very easily we can write this number of iterations in terms of k, because first 4 k iterations, second one k to the power of 1/3, then k to the power of 4/3. That's it. But what is the problem that we have? K here is not noun, because k is chosen randomly out of n numbers. Therefore, you do not know what k exactly is. Then since k is chosen randomly, then I will find expected value of x. Expected value of k to the power of 4/10. That's my goal. And my goal is to evaluate this. We want to know that this, what is the expected value of k to the power of 4/10. We had a formula for expected value. Let me recall you the formula. When you want to evaluate expected value of x, this is equal to sigma, say for example, of I from 1 to n, x equal I times probability of I. That's a formula that we have for evaluating expected value. If it looks hard, you can write, for example, I probability of I. That one works also. In this case, you have k to the power of 4 terms. Then when you want to evaluate expected value, the same formula can be used. We explained that expected value is nothing other than averaging. And here you are taking average, that's average. You are multiplying each outcome by the probability and add them. That's exactly something that we do for averaging. Here we do the same thing. Means you have sigma, k from 1 to n, k to the power of 4 tenths times probability of k. So what values k can accept? We explain here. K is this in this set, then the values that k can accept are 1, 2, till you go to n. And we explain again this. Because here k is chosen randomly, and we are choosing k uniformly. What does it mean when we say that we choose k uniformly? It means the probability of choosing 1, 2, 3, go to n are the same. And here we can say that the probability of 1 equal to probability of 2, go to probability of n, all of them are equal 1 over n. That's the meaning of uniform random variable. When we say that we choose a variable randomly, we choose k out of n numbers randomly, means that the probability of choosing each outcome is the same. Let's say suppose, for example, we want to choose one student here and pass this student without taking exam. Okay? We want to be nice. Then if we want to choose one student uniformly, it means your chance, the chance of all students here are the same. And that's a fair case. Then see, the same thing here. The chance of choosing each element among these 1, 2 to n are the same. Here I'm applying this value here. Then you can say this is equal to sigma k from 1 n k to the 4 tenth times 1 over n. And 1 over n is constant because it doesn't have k, it can be written outside. You have 1 over n sigma k from 1 to the power 2n k to the power of 4. That's my expectation. Then expected value for x is nothing other than 1 over n sigma k from 1 to n k to the power of 4. Any questions, any comments? Please ask. Again, I'm not sure if I'm pronouncing correctly or not. Sanjay, come on, pronounce correctly or maybe not. So, okay. Let me finish this study before we So, okay, that's the expected value. Expected value here is not enough because our main goal is not to find the expected value. The goal is to find the asymptotic expected value. Then in other words, we want to know that this expected value that we evaluated here asymptotically is same as what function. We want to know that this expected value asymptotically belongs to theta of what function. The goal is to fit this box. We had examples like this before. You have the summation sigma, then you just need to use the technique that we had, upper bound, lower bound technique that we had, and find the asymptotic value for this expected value. Then let's find. Okay, so this is the sigma that we have here. We have expected of x equal to 1 over n sigma k from 1 and k to the power of 4 times. If you want to find upper bound, then for finding upper bound, we can say that this is less than 1 over n sigma k from 1 to n to the power of 4 times. See, I replaced k with n, which is the maximum value for k. get the upper bound. This is the constant sigma, and we get 1 over n times n times n to the power of 4 here, n and n cancel each other, then we have n to the power of 4. That's the upper bound. If you want to find the lower bound, we will do the same thing, but considering half of the terms, then k 4/3, this guy is bigger than 1 over n sigma k from n over 2 to n k to the power of 4. It's going to consider half of the term. That's exactly the technique that we had before the foundation one at the beginning of the semester. We are dividing this by 2. So we can say this guy is bigger than 1 over n sigma k from n over 2 to n over 2 to the power of 4. As you can see, I replaced k with the bottom of this sigma. I replace k with the bottom of this. Do I have a constant sigma here? Then this guy equal to 1 over n times n minus n over 2 times n over 2 to the power of 4. N minus n over 2 is n over 2. We evaluate this guy, we have n over 2. Here n and n cancel each other. Then we have 1/2 to the power of 4 times n to the power of 4. As you can see here, upper bound is n to the power of 4 times, lower bound also is n to the power of 4 times. And here we can conclude expected value of x belongs to the theta of n to the power of expected value of x asymptotically is same as n to the power of 4. We got the same thing for the worst case. Then best case and worst case are the same. Then this example shows us sometimes best case and worst case are the same. Okay, I'm not sure if I'm going to correct this or you. So here, how many of us to correct me? So, shall we? Leo, that's an insane. Leo, that's an insane. Nicolas last semester today. Okay, so any questions, any comments? It is one example, easy example, to give us the idea that what we will have in the homework, in the exam. As you can see, the formulas that we had for evaluating expected value, all of them have been used here. Also, we could see that there are some problems for them. Worst case and best case are the same. We have some problems for them. Worst case and expected case are the same. And we will see we have some problems that best case and expected case are the same. I just want to explain about two notations that we will use them very often. One of them is this formula that expected case, expected is weaker than best case and weaker than worst case and stronger than best case. Worst case, expected case, worst case, and stronger than best case. Then what can be concluded if best running time, best running time is same as worst running time. You can say expected also is same as worst and same as best. Then if best case running time and worst case running time are the same, you have seen examples like this in Foundation 1 and this semester. And if you have some problems for those, best and worst are the same, then you can say expected also instead same as worst and best. In this example, best case was constant, worst case was n to the power of 4 that expected also was same as best. Worst case. Expected also was same as worst case. Okay, so let's see one more example to see these kind of problems better. What do we have here? Again, same story. As you can see, k is chosen randomly out of n numbers. You have, sorry about it, you have if else. If k is 1, we have this nested loop. If k is not 1, we have another nested loop. Here the goal is to find worst case running time, expected case running time, and maybe best case running time. All of them here can be evaluated. So again, see why expected makes sense. Talking about expected running time here makes sense. Because the number of times that you iterate, is not known. Why? Because k is chosen randomly. If k is equal to 1, the nested loops that we have in line 4 and line 5 should be considered. If k is not 1, then the nested loops that we have in line 10 and 11 must be considered. And we have absolutely no idea if k is 1 or k is not 1. Then I do not know what is the running time, what is the number of times that we iterate. Okay, let's consider first k equal 1. When k equal 1, we need to consider line 4 and line 5. In line 4 and line 5, as you can see, the number of iterations of line 4 is n. The number of iterations of line 5 also is n. Since you have a nested loop, then n times n is n squared. Therefore, if k equal 1, the number of iterations asymptotically is n squared. If k is not 1, means else will run, then the number of iterations in line 10 is n, in line 11 is log of n, then when we consider these together, the number of iterations is n log n. Then when k is not 1, number of iterations is n log n. When k is 1, number of iterations is n squared. Then here if I ask you what is the worst case running time, what your answer would be? What is the worst case running time? K equal 1, exactly, or n squared, exactly. And what is the best case running time? N log n. Then the worst case running time is n squared, best case running time is n log n. Because I just compared, you have two running times, n squared, n log n, and I just compare them. You see? Then you have n squared worst case running time, best case is n log n, because worst case was n squared, best case was n. That's it, very easy. Very easy. Okay, another holding giant. Okay, so probably you all recognize the GR